Space looks like the ultimate nothing. A black, silent emptiness stretching between stars and galaxies. A place so barren that even the word empty feels generous. But that picture is wrong in ways that are both beautiful and unsettling, because the void between things is not truly void at all, and that matters more than it first seems. By the end of this, you are going to see why empty space can bend light, create pressure, carry radiation, spark particles into existence for an instant, shape the structure of the cosmos, and even decide the fate of the universe on the largest scales. What looks like nothing is one of the most active, consequential things in existence. If you enjoy space videos that take huge ideas and make them feel clear and vivid, give the video a like and subscribe, but only if this is genuinely your kind of thing. And tell me in the comments where you are watching from. And one more thing. When you picture empty space, do you imagine it as truly empty, or as something more like a hidden ocean? I always love seeing where in the world these journeys are landing, and that question turns out to be more important than it sounds. So now, let us step away from planets, away from stars, away from the bright, obvious objects, and drift into the dark between them. What is actually out there when there seems to be nothing there at all? If all matter were removed from a region of space, would anything remain? Can emptiness have energy, structure, temperature, danger? And if space is not empty, then what exactly is the universe built on? At first glance, the idea seems simple. Space is what is left over when you take the stuff out. A planet is stuff. A star is stuff. A cloud of gas is stuff. Empty space is the absence of stuff. It sounds obvious enough that for much of human history, something like that was the default intuition. You look up at the night sky, see a few points of light, and everything between them appears to be a dark stage with nothing on it. Even now, that instinct is hard to shake. In everyday life, emptiness means no furniture in the room, no water in the glass, no cars on the road. So when we hear vacuum, we imagine perfect nothingness, a cosmic version of an empty container. But the universe does not really work like an empty container. The first crack in the idea appears the moment we remember that space is not just a backdrop. According to modern physics, space and time are woven together into space-time, and space-time is not passive. It can stretch, it can curve, it can ripple. Massive objects like stars and planets distort it, and that distortion is what we experience as gravity. Already, that means empty space is not merely absence. It is a physical arena with properties. A useful analogy is a landscape. If you roll a ball across a perfectly flat floor, the floor just supports the motion. But if the floor is actually a terrain full of slopes and curves, then the shape of that terrain guides where the ball goes. In Einstein's picture, planets orbit stars not because an invisible force reaches across a void like a cosmic hand, but because the space-time around the star is curved. Objects follow that curvature. In other words, even where there is no visible matter, the space itself still has geometry. It still does something. That alone is enough to change the old image. An empty space can be bent, and we know this is real because we see it. Light from distant galaxies is warped as it passes massive clusters of galaxies. Their gravity curves space-time so strongly that it acts like a lens, magnifying stretching and distorting the images behind them. Sometimes a single distant galaxy appears multiple times in the sky because its light has been split along different paths by curved space-time. Space is not a blank sheet. It is a shapeable medium. Then there are gravitational waves. When black holes collide or neutron stars spiral together, they shake space-time itself. These events send ripples across the universe, stretching and squeezing distances by tiny amounts as they pass through Earth. That is not matter, flying through space like debris from an explosion. It is the structure of space-time oscillating. The emptiness between objects can carry a wave. And yet this is still only the beginning, because when people ask whether space is empty, they usually mean something more practical. They mean, if I go far from stars and planets, is there really just nothing there? Not even close. Interplanetary space, the space between planets in a star system, contains sunlight, charged particles flowing from the sun, magnetic fields, dust, and occasional atoms from the thin outer atmospheres of planets or from comets shedding material into space. It is thin beyond anything we encounter on Earth, but it is not nothing. The solar wind is constantly streaming outward, carrying electrically charged particles across the solar system. Spacecraft do not drift through a pure void. They move through a very sparse but real environment. Go farther out, beyond the planets, beyond the heliosphere where the sun's influence weakens, and you enter interstellar space. That sounds emptier, and in some ways it is. But even there, the Milky Way is not made of stars floating in perfect nothingness. The galaxy contains diffuse gas, mostly hydrogen, with traces of helium and heavier elements, along with dust grains, cosmic rays, and magnetic fields. In some regions, the gas is compressed into dense molecular clouds where stars are born. In others, it is incredibly thin, but not absent. If you took a cubic centimeter of air at sea level on Earth, it would hold an astonishing number of molecules, far beyond everyday intuition. Interstellar space may contain only around a few atoms per cubic centimeter in many regions, and much less in others, which sounds like almost nothing by earthly standards. But stretch that almost nothing across trillions upon trillions of kilometers, and it becomes the raw material from which stars, planets, and eventually living things are made. Entire generations of stars are built out of matter that once drifted through what we casually call empty space. That is one of the first great perspective shifts here. Space can be unimaginably thin and still not be empty. Our sense of emptiness is often just a mismatch of scale. Think of fog. A very thin fog might look like clear air from a distance, but put a long enough beam of light through it, and its presence becomes obvious. Space is like that, except the fog can be so sparse that one atom may be separated from the next by large distances compared to anything in ordinary experience, yet over enough volume, enough time, and enough gravity, and that faint material matters enormously. This matters for travel, too. People sometimes imagine that if there were no atmosphere and no friction, space would be a kind of effortless highway. In some ways, it is. But spacecraft still have to contend with radiation, charged particles, micrometeoroids, and temperature extremes shaped by exposure to sunlight and shadow. Around planets, the environment can become much harsher. Near Earth, for example, There are belts of trapped charged particles held by our planet's magnetic field. These are dangerous enough that spacecraft and astronauts must plan around them carefully. The void is not just empty darkness. It can be a radiation storm with no air in it. And then there is the light. Light is so familiar that we often forget how strange it is that the darkness of space is full of it. Empty space can be crossed by electromagnetic radiation of every kind: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. A beam of light does not need air to travel. It moves through vacuum itself. That simple fact already tells us that vacuum is not nothing. It is a medium in the sense that it permits the propagation of fields and waves, though not a material medium like air or water. Radio signals from a spacecraft billions of kilometers away cross the darkness and arrive at Earth because space allows electromagnetic fields to evolve and carry information. The black between worlds is not blank. It is traversed constantly by radiation from stars, pulsars, galaxies, supernovae, and the afterglow of the Big Bang. That afterglow may be one of the most extraordinary examples of all. Everywhere in the universe, in every direction, space is filled with the cosmic microwave background. This is relic radiation from the early universe, released when the cosmos was young enough and hot enough that matter and light were tightly coupled, and then cool enough for light to finally travel freely. It is faint microwaves now, not visible light, but it fills all of space like a thermal whisper from nearly 14 billion years ago. This means that if you were floating in what you thought was perfect emptiness, the universe would still not be dark in a physical sense. Invisible microwaves would be passing through you from all directions, carrying information about the infant cosmos. The vacuum is bathed in ancient light, and that ancient light has a temperature about 2.7 degrees above absolute zero. That does not mean space has air with a temperature in the everyday sense. Temperature usually refers to the motion of particles in matter, and in a near vacuum, there are very few particles to share heat. But the radiation field itself has a thermal spectrum, and that gives the cosmos a kind of background temperature floor. Empty space is colder than anything in normal human experience, yet still not zero. Even the darkness is busy. Now let us go deeper, because so far we are still talking about things in space. Gas in space, dust in space, radiation in space, fields in space. But what about the vacuum itself, stripped as much as possible of particles and clutter? Surely that gets us to true emptiness. Classically, you might think yes. Remove all matter, block all radiation, cool everything down, and you should eventually reach perfect nothingness. A region with no particles, no light, no activity. But quantum physics does not permit such complete stillness. To understand why, we have to take one careful step into the quantum world without drowning in jargon. In everyday life, if something has exactly zero energy and nothing is happening, that feels stable and reasonable. But quantum physics says the universe at very small scales is governed by probabilities and limits on what can be known or fixed exactly at the same time. One expression of this is the uncertainty principle. Popular culture often reduces it to "you cannot know everything perfectly," which is not wrong. But here the more important point is that certain physical quantities cannot all sit at perfectly definite, unchanging values. There is built-in fuzziness. That fuzziness applies not only to particles, but also to fields. And in modern physics, fields are fundamental. The electron is associated with an electron field. Light is associated with the electromagnetic field. Other particles are associated with their own fields. These fields exist throughout space. A particle can be thought of, very roughly, as an excitation or ripple in its field. So what is the vacuum in quantum field theory? It is not the absence of fields. The fields are still there. The vacuum is the lowest energy state of those fields. That sounds peaceful, but because of quantum uncertainty, the fields cannot be perfectly frozen into complete stillness. Even in their lowest energy state, that they fluctuate. This is where the old image of nothing really starts to collapse. Quantum vacuum fluctuations are not little marbles popping in and out of a literal empty box in the crude cartoon version people sometimes imagine. The real mathematics is subtler and harder. But the key physical insight is that the vacuum has structure and activity. It is not a featureless zero. It has restless quantum behavior built into it. One way this is often described is through so-called virtual particles, temporary disturbances associated with interactions in quantum fields. This language can be useful, but it can also mislead if taken too literally. It does not mean tiny classical particles are constantly materializing like sparks from nowhere, and then vanishing in some miniature fireworks, show you could photograph if your camera were good enough. It is better to say that the vacuum state of quantum fields is not empty in the ordinary sense, and that this has measurable consequences. And measurable consequences are what matter. One of the most famous is the Casimir effect. If you place two extremely close, uncharged metal plates in a vacuum, quantum effects cause a tiny force that pushes them together. The intuitive explanation often given is that the plates restrict which vacuum fluctuations can exist between them compared with outside them, creating a pressure difference. The full story is mathematically more refined than that simple picture, but the important point remains. Something about the vacuum produces a real, measurable force. A setup that seems to involve nothing between the plates does not behave like nothing at all. Another example is the Lamb shift, a subtle change in the energy levels of hydrogen atoms that arises from interactions involving quantum fields and vacuum effects. This is not philosophical poetry. It is precision physics. The vacuum leaves fingerprints. Then there is Hawking radiation, which is often explained as virtual particle pairs forming near the event horizon of a black hole, with one escaping and one falling in. Again, that simple picture is not the full deep theory, and physicists themselves are careful about how literally to take it. But the broader idea stands. Quantum field effects in curved spacetime can make black holes radiate. A black hole, which once seemed like the ultimate one-way sink into darkness, is not completely black after all. The strange properties of the vacuum around intense gravity help give it a temperature and an evaporation process over immense timescales. So when people say empty space is boiling with quantum activity, there is a poetic truth there, but it must be handled carefully. The vacuum is not stuff in the familiar sense, and you cannot scoop it into a jar. Yet it is physically active enough that real experiments and real theories depend on it. Nothingness in modern physics is not simple. And there is an even more unsettling point. In quantum field theory, what counts as a particle can depend on the observer. This sounds absurd at first, but it comes from a deep fact. The concept of a particle is not always universal in curved space-time or for observers with different motion. A striking example is the Unruh effect, an observer accelerating through what an inertial observer would call vacuum may detect a bath of particles, almost as if acceleration turns emptiness warm. This is an extremely subtle theoretical effect, and not something we casually observe in daily life, but it drives home a profound message. The vacuum is not an obvious, fixed, universally agreed upon nothing. In some contexts, what one observer calls empty, another does not. That tells us we are dealing with a reality much stranger than intuition evolved to handle. And yet, if we step back, the weirdness begins to make a kind of sense. The universe is not built from little billiard balls moving through a passive emptiness. It is built from fields, geometry, interactions, and quantum states. Empty space is what remains when no ordinary particles are present. But what remains is still a physical entity rich enough to shape events. There is another forcefully practical demonstration of this. Space can push. Not in the science fiction sense of some invisible wind propelling ships, but in the sense that radiation exerts pressure. Light carries momentum. That is why sunlight can push on dust particles, influence the tails of comets, and even be used in solar sails, which gain thrust from photons striking large reflective surfaces. In deep space, this pressure is small, but over long times it matters. Again, what we call empty space turns out to be a place where momentum and energy are constantly being exchanged. Magnetic fields make the picture even richer. Planets have them. Stars have them. Galaxies have them. The interstellar and intergalactic space can be threaded by weak magnetic fields stretching over immense distances. Charged particles spiral around them, creating radiation, shaping cosmic plasmas, and influencing the flow of matter. If you could somehow see magnetic structure directly, the cosmos would look less like isolated lights in a blank dark, and more like an intricate web of glowing, invisible currents. And speaking of webs, on the largest scales, the universe itself has a kind of architecture that reveals how misleading the word empty can be. Galaxies are not sprinkled randomly. They gather into clusters, clusters into superclusters, and all of this forms the cosmic web. Immense filaments of matter stretching across hundreds of millions of light years, with vast voids between them. These cosmic voids are among the emptiest known regions of the universe. If any place deserves the title of emptiness, surely it is there. But even voids are not truly empty. They contain extremely low densities of matter, including dark matter, tenuous gas, and radiation fields. They still participate in the expansion of the universe. Light still crosses them. Quantum fields still exist there. Gravity still shapes them. Their emptiness is relative, not absolute. They are underdense regions, not nothingness carved out of reality. Dark matter adds another twist. We do not know exactly what dark matter is, but we know from strong evidence that it contributes much of the gravitating mass in galaxies and clusters. It does not shine, and it does not seem to interact with light the way ordinary matter does, which means huge amounts of the universe are filled with something invisible, a region of space that looks empty to the eye, may still be immersed in dark matter passing silently through it. The emptiness we see is limited by what our senses and instruments are tuned to detect. And then there is dark energy, perhaps the most dramatic reason of all that empty space may have profound physical properties. In the late 20th century, astronomers studying distant supernovae discovered that the expansion of the universe is accelerating, not just continuing from the Big Bang, but speeding up. Something on cosmic scales is driving galaxies apart ever faster. The simplest explanation, consistent with current observations, is a cosmological constant, effectively an energy associated with space itself. If that interpretation is right, then empty space has energy, even when stripped of ordinary matter and radiation. And because the amount of space increases as the universe expands, the total amount of this vacuum-like energy grows with it, leading to more accelerated expansion. This is one of the most astonishing ideas in all of science. The emptiness between galaxies may be the dominant ingredient governing the large-scale future of the universe. Now, this is where scientific responsibility matters, because there's a temptation to smooth over the mystery and speak as though everything is settled. It is not. We have strong evidence for the accelerated expansion. We have models that fit the data very well. But we do not yet know the underlying nature of dark energy. Is it truly a cosmological constant, an intrinsic energy of vacuum? Is it some slowly changing field? Is it a sign that our theory of gravity needs modification on the largest scales? These are open questions, and the vacuum energy problem is notorious. If you try to estimate vacuum energy from quantum field theory in a straightforward way, you run into a shocking mismatch with the observed cosmological value, one of the biggest known discrepancies between theory and observation in physics. Depending on exactly how the comparison is framed, the gap is absurdly large, the kind of mismatch that tells you not that science has failed, but that some deep piece of the puzzle is missing. That is a recurring pattern in this story. The closer we look at nothing, the less complete our understanding becomes. But before we get too lost in the edge of modern theory, let us return to something more tangible. What would empty space actually do to you? This is where the danger becomes real. If you were suddenly exposed to the vacuum of space without protection, you would not instantly explode, and your blood would not boil inside your veins in the cartoon way often shown in movies. The human body is tougher and stranger than that, but you would be in lethal trouble almost immediately. Without pressure, the water in exposed tissues can begin to vaporize. You would lose consciousness very quickly because there is no oxygen. Your lungs would be at severe risk if you tried to hold your breath. Extreme temperatures are part of the story too, but not in the simple way people imagine. In vacuum, there is no air to carry heat to or from your body by convection. So temperature exchange works mostly through radiation. Depending on sunlight and surroundings, or heating or cooling can happen, but suffocation and decompression are the immediate threats. This is another good reminder that empty space is not just empty. It is an environment with rules. There is no air pressure. There is intense radiation. There are no breathable molecules. Heat transfer behaves differently. Silence reigns because sound needs matter to travel through. The vacuum is not absence in the harmless sense. It is a hostile physical condition. Even spacecraft have to fight space constantly. They need shielding from radiation. They need thermal control because one side can bake in sunlight while another faces the cold of shadow. Tiny impacts from dust or micrometeoroids can become dangerous at high velocity. Electronics must survive charged particle environments that can scramble or damage them. In low Earth orbit, there is still enough thin atmosphere to create drag over time. At higher orbits, other hazards dominate. The engineering of space travel is, in large part, the engineering of surviving the notempty emptiness. And if we zoom out from human danger to cosmic processes, some of the most dramatic events in the universe depend on what fills this supposed nothingness. Stars are born in giant clouds drifting through interstellar space. Supernova explosions blast enriched material outward, seeding the surrounding medium with heavier elements. Shockwaves travel through gas and dust, compressing some regions and stirring turbulence in others. Cosmic rays race through the galaxy and interact with magnetic fields and matter. Black holes feed from disks of infalling gas and launch jets that punch through surrounding space for enormous distances. Galaxies moving through hot gas in clusters can have their own gas stripped away, like wind tearing leaves from a tree. None of this makes sense if space is treated as a pure absence. The environment between the obvious objects is part of the story, often the decisive part. Take the space between galaxies inside a galaxy cluster. It is not just dark emptiness. It can be filled with extremely hot, diffuse gas, reaching tens of millions of degrees, so thin that you would call it nearly empty, yet so vast that it outweighs the stars in the galaxies themselves. This gas shines in X-rays. It is one of the dominant visible components of many clusters. A region that looks black to human eyes can be blazing in wavelengths our eyes cannot see. That is another pattern worth pausing on. Human vision is narrow. We evolved to see a tiny slice of the electromagnetic spectrum useful under the sun on Earth. If you could see radio, microwave, infrared, ultraviolet, X-ray, and gamma-ray light all at once, the universe would look radically less empty. Invisible backgrounds, glowing plasmas, particle collisions, magnetic structures, warm dust, cold clouds, energetic jets, relic radiation. All of it would flood the sky. A great deal of cosmic emptiness is really an artifact of biological limitations. Our instruments have been correcting that illusion for more than a century. Radio telescopes reveal hydrogen spread across galaxies and beyond. Infrared observatories see dust and cool structures. X-ray telescopes show hot cluster gas, neutron stars, black hole environments. Microwave detectors map the oldest light in the universe. Particle detectors catch high-energy visitors from deep space. Every time we expand the senses of civilization, emptiness retreats. There is a philosophical temptation here to say that the universe abhors a vacuum, echoing an ancient phrase. But that old idea came from a very different picture of nature, and is not quite right either. The universe does have vacua in the physical sense. We can create very good vacuums in laboratories. Space is often a near vacuum. The point is not that vacuum cannot exist. The point is that vacuum is not synonymous with absolute nothingness. Absolute nothingness may be one of the slipperiest concepts we have ever invented. Even in pure philosophy, nothing is surprisingly difficult to define. Is nothing the absence of objects? The absence of space? The absence of laws? The absence of potential? The absence of mathematics? Physics usually does not deal in those ultimate metaphysical terms. It deals in operational terms, what can be measured, predicted, described by equations. In that language, the vacuum is a physical state, not a metaphysical void. And that distinction matters because many popular discussions blur it. When people hear that particles can appear from nothing, or that the universe came from nothing, they often imagine philosophers nothing, absolute non-being. But in physics, the word often refers to a vacuum state governed by laws and fields. That is not ordinary something, but it is also not the total absence of reality. If we do not keep those meanings separate, confusion spreads instantly. This becomes especially important in cosmology, where language can run ahead of certainty. There are hypotheses about the early universe in which quantum fields, inflation, and vacuum states play central roles. Inflation, for example, is the idea that the very early universe underwent a brief period of extremely rapid expansion. If some form of vacuum-like energy drove inflation, then once again what looks conceptually like emptiness could have tremendous dynamical power. Inflation helps explain several observed features of the universe, and it is strongly supported in broad outline by evidence, though the exact mechanism and field responsible remain uncertain. Here too, empty space can behave less like absence and more like an active agent in cosmic evolution. Then there is the idea of false vacuum and true vacuum, one of the more dramatic possibilities in fundamental physics. Very roughly, a false vacuum would be a state that looks stable, but is not the absolute lowest possible energy state. If our universe were in such a metastable state, then in principle, a transition to a lower energy vacuum could occur. Popular retellings of this idea can become sensational very quickly. So let us keep it grounded. This is a theoretical possibility discussed in some models, connected in part to the measured properties of particles like the Higgs boson and top quark. But the conclusions depend on assumptions and extrapolations far beyond directly tested energies. There is no evidence that such a vacuum decay event is about to happen, and there is no practical reason to lose sleep over it. Still, the mere fact that physicists can seriously discuss different vacuum states should tell you how rich the concept of nothing has become. The vacuum is not a blank. It may have phases. Imagine discovering that an empty room could freeze, melt, crystallize, or collapse without any furniture in it. That sounds impossible only because our everyday word empty carries the wrong intuition into realms where it does not belong. Another strange and beautiful fact is that vacuum can polarize. In very strong electromagnetic fields, such as those near certain exotic astrophysical objects like magnetars, quantum electrodynamics predicts that the vacuum itself can behave in ways that affect how light travels, a phenomenon known as vacuum birefringence. The effect is extraordinarily subtle under ordinary conditions, but in extreme environments, the vacuum can act almost like an optical medium. Again, not because it is full of ordinary matter, but because the quantum fields that define the vacuum respond to intense conditions. Even light can notice the properties of emptiness. This is one reason magnetars are so fascinating. These are neutron stars with magnetic fields so immense that they push physics into regimes barely imaginable on Earth. The surroundings of a magnetar are not a simple empty stage. They are places where the vacuum itself may reveal non-linear behavior. The universe keeps taking the thing we call nothing and turning it into an actor. There is also a curious thermodynamic side to emptiness. We have already mentioned that the cosmic microwave background gives the universe a baseline radiation temperature. But in general, space near an object can be hot or cold, depending on radiation and environment. Astronauts in sunlight can heat rapidly, while shaded areas stay bitterly cold. Dust grains in space find equilibrium temperatures based on absorbed and emitted radiation. Planets without thick atmospheres can swing between extremes because there is no dense air to redistribute heat. The vacuum does not transfer heat by direct contact the way air or water does, but it does not remove thermodynamics from the picture. Instead, it changes the rules of the game. Around black holes and neutron stars, the emptiness nearby can host some of the most violent phenomena in nature. Matter in accretion disks is heated to enormous temperatures. Magnetic fields twist and reconnect. Jets launched near black holes can accelerate particles to tremendous energies and punch across interstellar or even intergalactic distances. In quasars, a supermassive black hole at a galaxy's center can outshine the stars of the entire galaxy, all because matter falling through surrounding space is converted into radiation with incredible efficiency. The darkness around the monster is not passive. It is the arena in which extreme gravity, plasma, and fields interact. Even the notion of color in space is deceptive. Human eyes would see much of deep space as black because the gas is too thin to glow brightly to us, and because our eyes are poor detectors in low light. But long exposure images, false color observations, and non-visible wavelengths reveal structure everywhere. Nebulae stretch in ghostly filaments. Diffuse hydrogen clouds span huge regions. Shock fronts sweep through stellar debris. Interacting galaxies pull out tidal streams of stars and gas. Our impression of empty space often says more about the limitations of direct human perception than about the true state of the cosmos. And yet, despite all of that, there is still a meaningful sense in which space is astonishingly empty. That tension is important. Saying space is not empty does not mean space is crowded like a city street. It means that our binary categories fail. The universe contains regions so sparse that ordinary human language strains to describe them. Most of the volume of an atom is empty, in the sense that the nucleus is tiny compared with the electron cloud. Most of the volume of the solar system is empty compared with the sizes of planets. Most of the volume of galaxies is empty compared with the stars. Most of the large-scale universe is low-density space between concentrated structures. The emptiness is real as a matter of relative density and spacing. It is just not absolute non-existence. That distinction may sound subtle, but it changes everything. A cathedral can feel empty even when sunlight, dust motes, air currents, sound, magnetic fields, and heat all move through it. Space is like that, but stripped of familiar matter and inflated to impossible scales. The silence is real. The distances are real. The sparseness is real. But hidden within that sparseness are laws, fields, radiation, geometry, particles, and energies that do not stop existing just because there is no air to breathe. If you were to travel far from any star, far into intergalactic space, the emotional experience would probably match our intuition of emptiness. It would feel like exile from everything warm and bright. The nearest galaxy might be millions of light years away. Stars would no longer crowd the sky in familiar ways. You would be immersed in blackness so deep that language would start to fail. Yet even there, photons from ancient epochs would still cross your path. Dark matter might stream through your body unnoticed. Quantum fields would still permeate the region. Space-time would still have geometry and expansion. The cosmic web would still shape the broader structure around you. You would be in one of the emptiest places imaginable, and still not in nothing. This is one of the reasons astronomy is so good at humbling intuition. The brain evolved to throw stones, read faces, and avoid cliffs. It did not evolve to understand a vacuum fluctuation or a billion light-year filament of matter. We naturally import common-sense words like empty, dark, still, cold, and nothing into cosmic contexts, and those words break under pressure. Astronomy keeps teaching the same lesson in different forms. The universe is under no obligation to fit the categories that worked around campfires. Consider the atom for a moment, because it offers a smaller mirror of the same surprise. If the nucleus of an atom were scaled up to the size of a marble, the electrons would be far away relative to it, and most of the atom's volume would seem empty. Yet that empty-looking region is where the quantum structure of the atom lives. It determines chemistry. It governs how atoms bond, how solids exist, how light is absorbed and emitted. The empty part is functionally everything. Likewise, on cosmic scales, the spaces between things are where interactions unfold, where light travels, where gravity operates, where galaxies are embedded, where vacuum energy may dominate. The apparently empty part is not secondary scenery. It is the stage on which the play depends, and the stage itself may be evolving. The universe is expanding, which means large-scale distances between unbound galaxies grow over time. Space is not merely containing objects while sitting still. The metric of space-time itself changes. This can be a slippery idea because our intuition wants to picture galaxies moving through pre-existing emptiness, like shrapnel through air after an explosion. But on large scales, the better picture is that the space between galaxies expands. Over billions of years, that changes the observable universe. Distant galaxies shift, redshift increases, and in the far future, many galaxies now visible may slip beyond the cosmic horizon, and leaving local observers in a much lonelier-looking cosmos. In that future, emptiness becomes even more dominant to perception. The night sky for distant descendants, if any exist then, could be far poorer in visible galaxies than ours is now. The universe would not necessarily be emptier in the deep physical sense we have been discussing, but it could look far emptier. Space would keep asserting itself not as a background, but as a governing reality. And here we arrive at one of the most profound reversals in modern science. For a long time, matter seemed primary and space seemed secondary. You had objects, and then you had the gap between objects. But the deeper physics goes, the more that hierarchy blurs. Fields fill space. Geometry is dynamical. Vacuum states matter. Expansion matters. Dark energy may be energy of space itself. In some approaches to quantum gravity, Spacetime may even be emergent from something more fundamental, though that remains deeply speculative and unfinished. We are not just placing things into emptiness. We are trying to understand a universe in which the emptiness has its own reality. This does not mean every mystery headline about space is trustworthy. It is easy to take terms like quantum foam, virtual particles, vacuum energy, or space-time fabric, and turn them into mystical slogans. That is exactly what we should resist. The truth is more satisfying than exaggeration, because it is both stranger and more disciplined. We know many things with confidence. Space carries radiation. It has geometry. It hosts fields. Vacuum effects are measurable. The universe's expansion accelerates. We also know that some of the deepest questions remain unresolved. What exactly is dark energy? How should vacuum energy be understood in a complete theory? What happens when quantum theory and gravity are fully unified? Those are not gaps for fantasy to rush into. They are frontiers. That frontier feeling has been with this subject from the beginning. Every time science tried to pin down what a vacuum really is, the answer grew richer. Ancient debates about whether a void could exist gave way to experiments on air pressure and vacuums in laboratories. Classical electromagnetism turned empty space into a place where electric and magnetic fields live. Relativity turned it into a dynamical geometry. Quantum theory turned it into a fluctuating ground state. Done it. Cosmology turned it into something that may drive the acceleration of the entire universe. At no point did emptiness become simpler. Instead, the nothing kept accumulating consequences. There is a practical lesson in that. In science, a thing can look absent because it is thin, invisible, difficult to detect, or conceptually hidden. The history of astronomy is filled with these mistaken absences. We once thought the Milky Way was the universe. It was not. We once thought galaxies might be distributed in a fairly straightforward way. They were not. We once thought the expansion of the universe should be slowing under gravity. It was not. We once thought black holes were likely just mathematical curiosities. They were not. Again and again, the cosmos waits behind easy assumptions and then overturns them. Empty space may be one of the oldest easy assumptions of all, and there is a certain emotional power in that. It means the dark is not just dark. The silence is not just silence. The places where nothing seems to be happening may be the places where the deepest laws are laid bare. Space strips away the distractions of ordinary matter and leaves us face to face with the underlying machinery. Fields, curvature, radiation, quantum fluctuations, expansion. It is like turning down the noise and discovering that the background hum is the real song. If you have ever looked up at a clean night sky and felt both wonder and unease, this may be part of the reason. The blackness between stars feels like a mystery because, in a real sense, it is one. Not merely because we do not know what is there, but because what is there refuses to fit everyday categories. It is physically present without being tangible in the old way. It is active without being crowded. It is full without being full of familiar things. Even language begins to fail around this. We say space is full of fields, but field is a word borrowed from something else. We say space-time bends, but bend is an analogy. We say virtual particles pop in and out, but that is a compressed teaching image, not the underlying mathematics. We say vacuum energy, but energy itself is one of those terms that everyone uses and few visualize correctly. Part of doing this honestly is admitting that our words are ladders, not destinations. They get us closer, but the reality remains subtler than the language. That subtlety should not discourage wonder. It should deepen it. Because there is something extraordinary about the fact that human beings, standing on a thin skin of rock under one modest star, have figured out that the void between galaxies is not empty. That light from the early universe still fills all directions. That black holes can radiate. That gravity is geometry. That the expansion of the cosmos may be driven by the energy of space itself. We are tiny, yes, but we are not blind. We have learned to interrogate the dark, and the dark has answered, though never simply. The answers also change how we think about absence closer to home. The air in your room feels ordinary, but remove it, and the room does not become philosophical nothingness. It becomes vacuum, with pressure differences and thermal consequences, radiation passing through, fields still present. Likewise, remove stars from a region of the sky, and you do not get a hole in reality. You get a different physical state, one that may be sparse, cold, and lethal, but still profoundly structured. Nature does not seem fond of absolute blankness. There may even be a psychological reason we keep imagining empty space as true emptiness. Human perception is object-focused. We notice things more easily than relations, containers, backgrounds, or continuous fields. A tree stands out more than the air around it. A planet stands out more than the gravity well it inhabits. A galaxy stands out more than the dark matter halo enveloping it. But science often advances by making the unseen context visible. The context is where causes hide. In cosmology, the context is everything, but galaxies move the way they do because of the mass and geometry around them. Light arrives distorted because of space-time it crossed. The universe evolves the way it does because of its total energy content, including the parts we cannot see directly. Even the fate of the cosmos may be written not in the stars themselves, but in the character of the vacuum between them. That raises a quietly profound possibility. Perhaps what we call empty space is not the leftover part of the universe. Perhaps it is one of the central characters, and matter is only the brighter, denser punctuation written into it. There is a kind of poetry in that, but it is not empty poetry. It is grounded in observation, theory, and the hard-won humility of modern physics. Think again about what your eyes see on a clear night. A handful of stars, maybe the pale band of the Milky Way. Darkness almost everywhere else. It feels natural to interpret that darkness as absence, but within it lie the magnetic scaffolds of the galaxy, drifting hydrogen atoms, high-speed cosmic rays, relic microwave photons from the early universe, space-time curvature from masses near and far, quantum fields in their vacuum state, perhaps vacuum energy itself helping accelerate the expansion of the cosmos. The black is crowded with significance, and still, for all that, it remains hauntingly spare. That is what makes space so emotionally powerful. It is not a packed aquarium where every inch is visually busy. It is a cathedral of low density, where immense silence coexists with invisible activity. The emptiness you feel is real enough to move you, but the physics beneath it is rich enough to overturn that feeling. Both responses belong there. the emotional impression of void, and the scientific realization that the void is alive with structure. In the end, this is what empty space reveals about the universe. The cosmos is not built from simple opposites, like something and nothing, full and empty, presence and absence. It is built from layers of reality that only look simple from far away. The farther science has gone, the more it has shown that apparent emptiness can hold the deepest truths. The dark between stars is where light travels. The vacuum around black holes helps define their fate. The low density reaches between galaxies may contain the clue to why the universe expands the way it does. Oneness, what seems like absence becomes explanation. There is also something quietly human in that lesson. We often overlook what does not announce itself. The background, the silence, the space between obvious things. But the universe keeps insisting that the background matters. Sometimes the background is the thing doing the work. Sometimes the silence is carrying the oldest signal in existence. Sometimes the emptiness is where the mystery lives. So the next time you hear someone say that space is empty, it is worth pausing for a second. Empty compared with Earth, yes. Empty compared with a star, absolutely. Empty in the sense of being a perfect nothingness, not at all. It has shape, energy, fields, radiation, danger, history, and maybe the key to the future of the universe itself. The void is real, but it is not blank. And perhaps that is one of the most beautiful patterns in astronomy. Again and again, the universe takes the thing that looks barren and reveals hidden depth inside it. A faint smudge becomes a galaxy. A black point becomes a black hole. A silent sky becomes a relic glow from the birth of the cosmos. And empty space becomes one of the strangest physical realities we know. The darkness between the stars is not where the universe ends. It is where some of its deepest stories begin. Thank you for being here with me for this one. And if you made it all the way to the end, I am glad we got to look into the so-called emptiness together.